why network mapping? For the blue teams or the defensor, do research to this, like we are going here, to know its network, and to view its user facing the internet, clicking on every download button, extra, and doing. And that's why we have some stuff to do. And for the red team attackants, we can retrieve information on a given target. We can observe a target over time. That is to say, we scan it, and then a month after we scan it, and we do the difference. It's a way to find potential low-hanging fruits, or in a pen test to give a first element to view and then dig in. So yes, keep calm. Yes, we scan. So the principle is quite easy. We analyze the target to retrieve the most accurate image. To doing this, we use tools like the well-known Nmap. So we send probes, that is to say ping or ICMP packets, etc. And we just see what the host responds to us, if it responds, and what is his answer. Do we have HTTP server, FTP server, etc.? And it is Apache, it is Nginx, etc. So we also have to know that we have some biases, because I'm making my scan from my home. Maybe my internet provider will just cut some packets, or the target may have a firewall. My IP can be filtered, or the target may want to show me something that is wrong. And the tool we use, so for instance, Nmap by default just scans the top 1,000 ports that he considers as the most frequent. So these last years, even if I'm very young, but I do know floppy disk. With growing internet capabilities, we can now have faster scans, and we can now scan the entire internet, an entire country, a whole enterprise very quickly. So that's the good part, but the bad part is that we have a lot of results to analyze. And contrary to other countries, we can have many people to do this, but we have many cores. So we will use these cores instead of these people. First, we need to have this data, so we don't want to get them, to parse them. That's the hard part, and we're too full for this. So there are tools to deal with. So for instance, there are scans.io. It's a very good source of data, but we want to use our own. Then there's the well-known Shodan, with a very good API, a nice-looking interface, but we don't want our result in the cloud. Then you have Zoomai, if you know. This is the Chinese version of Shodan, of course. Of course, there is one. And Quarks Lab IVID, but it's private. And thanks to Snowden, there is the GCHQ agenda, ex-UK top secret. And finally, we come to Ivre, drunk in English, which is open source, developed also by our colleague. And it's the one we will use. So the sample we will use today, and that you can use too, is the worldwide Modbus scan. That is to say, Modbus is a kind of control and command protocol for SCADA. And this is a scan of the whole internet, and keeping the whole routable internet, keeping only the targets responding to our probes with a look like a Modbus service. And if you want to reproduce this result, you can get the sample here. So the agenda for today, you just quickly introduce Ivre and manually digging. Then you will talk about the hard stuff, mathematics and all this magic. And we go back to results. So Ivre, this stands for Instrument de veille sur le réseau extérieur. And the punchline is Ivre il scan Internet. That's for French. There is also the name in English, which is drunk, for digital recognition and not network, of course. It's managed passive and active, but we will just focus on the active part, and it uses common technologies. For instance, directly, you can say, okay, let's scan a country, for instance, the Albania, just 1,000 hosts. Then, once the scan has been done, get the results into our database, and please parse these results. So here, this is sample host, and it's look like what Nmap give you. You have the result of host scripts and for each open ports, the corresponding service script. And that's what you will use. So you just write an API, just say, okay, I want only in this autonomous system, I just want the host with this port and this port, give me them, and then we will work on this. And we don't have to manage the getting and passing data. So what about manually digging? This is what we have done until today. So yeah, this is the web interface. This is just for chatting. Here we are only we only have the Modbus scan and only host with at least one open port. So the first thing we can do look for is the address space. So I don't know if you see it. It is a representation, a graphics of on the first axis the EV bytes, and on the second axis you have only the last byte. And the colors correspond to the number of ports opened. So you can see that even it's a scan on /0, the repartition is not equiparable. Equally reparted, that's the one. For instance, we can look for the map repartition, and area there is no this equally repartition. Something like this. The main targets are located in the Europe and the United States. Let's look for a country in Europe and remap. And you can see that mainly. Oh, there is people here, maybe. Okay, so let's go back to the whole world and look for top ports. Remember, we have our bias. It's that we only have scan the Modbus device. So, of course, every sample, every host has the Modbus port open. But actually, it's not relevant information. It is our bias. Then maybe look for top autonomous system. Well, forget about us, not autonomous system. I don't want to talk about Orange. So maybe top country. And as usual, the United States are at the top, but the Turkey is at the second place, which is very unusual. If we use a random scan on the internet and we'll do the same, that's what the curve looks like usually. So United States, then China, then Korea, then Germany, etc. So back to our Modbus scan. If we focus on the Turkey, we can now maybe look for top services that are not very frequent, the top-bottom service, and maybe, I don't know if you know, top HTTP. Don't know what it is. So we have only one in the whole Turkey that have these services. Well, I don't know what it is, but I think it's very good, but it's marked as safe, so we don't click. Okay, let's go back to the slide. So that's what we can have by just manually digging. So we can quickly find some interesting results. There are interesting results to find, but it mostly relies on the analyzer knowledge, and this is a human bias. I don't know if you have seen, but there is 10,000 of targets, so of hosts to see. So it can be very time-consuming to look for. And what we want, it's maybe an automatic grouping of similar hosts. That is to say, if I look for a host which is a web server with common host, with common service and common products, I don't want to have to do the same for every a web server, which looks like it. So a first part can be to automatically group similar hosts. So we just have to look for each one of them, each of each group, one of each group. And a second wish can be to have a way of highlight uncommon host. That's to say, products that are very different, hosts that are very different from each other. And machine learning via clustering anomaly detection can answer that. So that's why Xavier.
Okay, so at the beginning of my stage, I didn't know anything about machine learning. The only thing that I thought is the machine learning was more about the picture on the left. Actually, it's more about the picture on the right. So what is machine learning? It's a field derived from the pattern recognition and artificial intelligence. It's closely related to computational statistics, but hopefully for us, the smart guys, the smart mathematicians, have already done the work, the hard work. They have made a lot of papers, and mostly all of the algorithms that we will need are already implemented for your language. So we just have to use this algorithm and just pick the right one and use it correctly. Machine learning can be divided in two main categories. That's not exhaustive, but that's the main categories. The first one is supervised learning. So basically, it's when you, for instance, you have an algorithm that will try to recon some picture you gave to it. So in the first stage, you will give him a picture of a cow. You say that this is a cow. The algorithm will learn. Then you give it another picture, for instance, a beer, and you say that you can drink it. This is a beer. And in the second stage, you give him a new picture and you ask, what is it? Is it a cow? Is it a beer? So this is great, but sadly, it does not fit to our needs because we have a lot of scan, a lot of machine that we have. And if we would like to use supervised machine learning algorithm, then we would have to manually label all our hosts. So consider if you have 10,000 hosts, it will be really time consuming, and we are lazy, we don't want to do that. And the second thing is, by doing this, you will introduce bias. That is to say that you will tell the algorithm this should be considered as a printer, this should be considered as a web server. And if you do that, you lose the great thing about machine learning and trying the algorithm to find by himself what it is. So we use the second categories, which is unsupervised machine learning algorithm. It's really much the same thing, just you don't have to set the label first. So the algorithm will try to find it by himself, and sometimes it will even find something that the human eye would not have seen by himself. So it can find hidden patterns, and that's something that we're interested. So remember, we have three things that we want to do, to be able to do. The first one is grouping hosts by similarities, because we don't want to analyze every host in the database. We just want to analyze group of hosts, like this one, and I know all other hosts in the same group are kind of the same, so we don't have to do the work 10,000 times. So that's done by the clustering algorithm. The second thing is emphasizing uncommon hosts or anomalies, and possibly something weird is happening. So it is anomaly detection algorithm. And the third thing we would like to do is representing the results, because as Camille said, we just do the scanning with Nmap, and if you just put normal parameters to Nmap, it will scan the 1,000 most common ports according to Nmap. So we will have a 1,000-dimension vector space, and you can't represent that in 2 or 3 dimension easily. And that's what principal component analysis is for, because if you can represent the data, it is more easy for you to understand what the scan is. So we have 2 problems. The first one is that what we have is scan result, Nmap result, as we showed before. And what the algorithm that are actually already written want in input are matrices. So the hard work is how to transmute the scan result into algorithm matrices. So that's doing that. The difficult part is to do that relevantly. So we had several approaches for that. You can say experimental or incremental if you're optimist. The first one is a binary solution. that was encouraging, but with patchy results, it can be improved. So what it is you take a host that your scan result have given to you, and you look at the 1,000 most common port that Nmap tells you. Nmaps will tell you the state, those products, what is on it, is it the open SSH server. You just look, is it open or is it closed? And if it's open, you put a 1. If it's closed, you put a 0, like this. So it gives good results. The servers are grouping together. There is some anomaly that will appear, but sadly, you can't do something. Consider this. If you have the host number 1 who is normal, with on the port 22 open SSH server, and port 80 an Apache server. But the second host is more weird because on the port 22 there is not a SSH server, it's Nmap daemon. This is really weird, but if you consider the fact that we put 1 if it's open and a 0 if it's closed, the two hosts are exactly the same for our algorithm, and we won't spot this abnormality. So what we did was trying with frequency solution. It's basically you will beyond your scan, beyond your wall scan, you'll just check the frequency of operation of one service, like OpenSSH. So it will be really common on the port 22. And when you have one host with an Nmap daemon working on the port 22, this is really uncommon. So if you put the frequency, this is what you get. I put 0.99 for the TCP one because most of the time this port is closed, and if one time one host had this port open, this will be really uncommon. So the algorithm will find that this is uncommon and will highlight this. So we speak about the 3 algorithms we used. The first one that I will speak about is the principal component analysis. It's about representing data which are in high dimension space to 2 or 3 dimension space for our case. And while doing that, we'll try to keep the relevant information. So what interests us. So here you have sample in 2 dimensions, and you can see that the relevant part of information or the variance is gathered in 1 dimension. So there is 2 axes. The length of the axis represent the quantity of information you get. So if you do the projection of on the first axis, you will lose about 5% of information, but you will divide the dimension by 2. And doing that, you can print in a relevant way data in a high dimension. So this can be used on a real-world example. So this is a study about what the people in England, Northern Ireland, Scotland, and Wales will usually drink and eat. There is 17 pointer, so 17 dimension. And if you look just like this in the tabular, you won't see a relevant thing, or you won't see a real trend for one country to be really different from one or another. But if you do the PCA on those data, here what you get, that's in 1 dimension. So clearly the Northern Ireland seems to be different, really different from Wales, England, and Scotland. If you do that in 2 dimensions, you lose a bit less information, and you have the same result that Northern Ireland seems to be different. If we go back to the real data, we can see that, for instance, Northern Irish people eat way less fruit than the others, but they eat way more fresh potatoes, and I think they drink a bit less also. So that's what the PCA found relevant and decided to show us in the representation. And for those of you who are as bad at geography as I am, just remember that the Northern Ireland is the only one that is not on the British island. So it may be related. We will do a quick overview of this. So we've got a tool, which is Analyzer Tree. So we say that we want the Modbus scan. We limit to 1,000 hosts to be a bit quicker, and we want only hosts with 0 to 10 port open. So we have 1,000 hosts. And we plot that in 2 dimensions. Here's what you get. So, okay. So on the right, if you can see, there is the decomposition of the axis. It means what the axis actually represent. So for the first axis, the x-axis, you see that the port 23, 21, and 22, so Telnet, OpenSSH, and SFTP, are the port that are actually matters for the first dimensions. If we get back on the representation, you can see that there seems to be 3 clusters from left to right, and that probably represent host with OpenSSH, SFTP, and Telnet. And that's the same story for the second dimension with port 4043 and 22, so servers with HTTPS and OpenSSH, or SSH, actually. Okay, so yeah, we can plot the same thing in 3 dimension, and we'll see that there is one more information that is given for the third dimension. Here, clearly, this is the machine that have the port 8080 responding to the probes. And if we plot in 3 dimension, we will see that it will split those hosts in 2 groups. Those who have something running on the port 8080 and those who have not. So the third dimension actually brings something new, new information that you lose when you do the PCA in 2 dimension. And so that's really useful for printing data and getting the point of view of what is actually running on the scan. But the algorithm we do, they will run on a high dimensional vector space, so they won't lose information that the PCA will get you lost. So the second algorithm we will speak about is the clustering algorithm. So it's about grouping elements by similarities. Like I said, if you have 1,000 servers that are actually really close from each other, you don't want to spend much time on working on 1,000 web server. You just want to get one, see what it is, and then pass to another group. So this could be easily done by a human if the data were easily represented in 2 dimension or 3 dimension, because you just have to make cluster by yourself. But because we work in a high vector space, the clustering algorithm works well and better than I. Here's an example. So we'll take 64 dimension to represent a number. So the number is on the top, on the bottom right corner. So 64 dimension, that's actually 64 pixel. And 1 pixel can take 256 possible values. So it's a grayscale. You put them together, you get a number. So that's 1 sample. And if you take several samples, like this, and you give it to a clustering algorithm. We took Camille algorithm for this example. You ask him to make 10 cluster, and then you ask what is a cluster. So by what is a cluster, I mean give me the representation of a cluster, or give me the mean of a cluster. So it will give you a matrix. And this matrix, you do exactly the same. So you take the number in the matrix as pixel, you put the pixel together, and that's your image. And so that is what the algorithm tells you. So you can actually get your numbers by that. So we use Camille for, so Camille was the algorithm we just showed. We used it for our tool because it scales well in high dimension. It is easily parallelizable. And we also, we'll do a quick, okay, so with Camille, you have to tell how many clusters you want. So Camille will just add, I don't know, 3-4 clusters, okay. Then we run the algorithm, and it will try to lower as much as it can the mean between the centroid and all the other dots in the cluster. You see that it will tend to a stable. But that's not really convincing. This is not what we would like to do. So there is another algorithm we use, which is dbScan. It's closer to what the human eye would do because it's based on density. And on one other advantage of that dbScan algorithm is that it can detect outliers. So we'll make a quick overview of the algorithm. Okay. So basically, there is two parameters that you can give to this, which is the length between two samples to be considered as close from each other, and how many dots, how many samples you want to be a group. So here the length is 1, and the mean points for a group to be considered as a group is 4. So if you have three points, three samples somewhere in the corner, they won't be considered as a group, and it will be anomalies. Okay, so this works better, and normally you will have new cluster for the eye and for the mouse. Okay. So we'll show this. So maybe you can do a Camille's algorithm. So we cluster the host with, okay, 3, maybe 3, because we had like 3 cluster when we watched it together previously. Okay, so we can plot this in 2 dimension. Okay, so as you can see, it's a bit melted. Maybe it's because we lose information by plotting this in 2 dimension, and if we do that in 3 dimension, maybe we will be able to see why the algorithm picks those points. It's a bit clearer now. You can see that the 3rd dimension actually was counting, and that's what the algorithm took. Okay. Okay, so the last algorithm we will speak about is the anomaly detection. Why anomaly? Because anomaly is not something that is far from mean. Here you have a picture where the anomaly is exactly the mean. So we just cannot take all the points and say, okay, what is the point which is the farther from the mean, and this is an anomaly. No, it's not that simpler. So there is basically 2 kind of approaches. The one with you consider that your data are Gaussian reported, but we cannot make this assumption. And the other one is the one-class support vector machine. At least that is the one we choose to use in the work. Yeah, we have to provide the anomaly portion for that to work. This is effective in large dimension vector space. And okay, so we'll show you how it works still on our tool. Okay, so we have 1,000 hosts, and we want to search anomaly. So he's searching the 10 most uncommon hosts, and that's what we get. We will get back to the web view to analyze further in detail those anomalies. So as you can see on the top left, we have 10 results selected. That's our 10 anomalies. And if you look closely to one anomaly, you'll see that something weird is happening. Like the ports that are open are not the port that a real machine, or at least a standard machine, would have. Okay. Okay, I'll let Camille take the rest.
Okay, so some quick results. Okay. So just going back and forth from the web UI and the analyzer client. So just beginning with a manual digging of an expert. Thank you, Xavier. So let's go with, for instance, a scan of a latent country, but with a lot of bank, that is to say Luxembourg. No, Luxembourg. Like Luxembourg. Okay, so maybe the address space. Okay, that's... Okay, so maybe I start with another one. Maybe let's go with the random scanner instead of Luxembourg. Too many points. Demo effect, of course. Entrée. No. No. Just okay. Thank you. Demo effect, of course. It always happens. So. Okay. Oh, please, please. Not the time. That's the mode porn. Porn mode. Sorry. Okay, so. Yes, I do know. Okay, so the IP addresses. There is a band that seems to not be used. So let's select it. Yep. And now we can go to the analyzer tree with this filter and just look for what's happening in this range of IP. Okay, so that was my shell. You take your time. Okay, so plot in 2D. Mentioned, yes. So, well, we have, if you look for points, there is 2 points that are very, very uncommon and a big pack. So let's just do a clustering in 2 dimension. And account. So on one cluster we just have one guy, and the other one in the cluster 0. So let's select this guy and see what it looks like. And white is very uncommon. And this is because he got a lot of open pore. So actually, this is what we have seen as maybe trivial honeypots, because this host seems to just respond with a random value, which is sometimes open, sometimes closed, but it's just a loss of time to consider it. So if we take a bigger scan, just so the whole random scan, just no. In the analyzer tree, please. And so go back. Yeah. No. What is he doing? Okay. So plot in 2 dimension again, but there is more host now, about 10,000. And what we do have is a pack of hosts like before, and a lot of points that are not in this pack. And if we, like before, we just do our Camille clustering quickly, maybe for two elements. We want to just eliminate these hosts because they are not interesting. And if we remove them, when we plot again, we go back to a common with a common graphics, which are very more interesting, and we do not lose our time on these trivial honeypots. So last example, which this one is on Luxembourg. So go in the web interface maybe, and let's start with the category Luxembourg. And we are looking for targeting an autonomous system. So let's see what are the existing autonomous systems. So maybe the Foundation Restina, because there are not too many hosts. Now we'll do on it maybe a DB scan algorithm. So go back and forth, yes, use the filter, use the shell. And so, yep. So remember, the DB scan is the second algorithm, the one which is doing his stuff like the human eyes, and he has advantage that already he also come with an anomaly detection. So just select a cluster. So for instance, the 8. Actually, this is not deterministic. So okay. So I'm not sure of what we will found. But the idea is that it detects around 20 categories. So for him, we just have to look to each category and then to the noise. So here we may have the host with the 8080 port open and maybe a HTTP server on it. So if we look for a second cluster, back on the analyzer clear, so maybe the 9, we'll have another category with a different host. And this time, this is, I don't know, maybe we have them, maybe not. You take your time. Okay, so this time it seems to be the host with the 22 and 25 open. Okay, so we can now. So now we have several categories. We have to look just for one of each, and we have noise or outlier or anomaly. So just select the anomaly. Here, this is the noise, I think. So we have around 1,000 of it. And yes, please. Oof. And hope it will not crash my browser or my assistant.
If you crash, you have to use yourself as a weapon.
Yeah.
Use the Wassenaar Treaty.
And so what we got here, we have several hosts which are all different. Looking for this one maybe. What we got, the AOL server HTTPD. I don't know if you know it. And maybe if you look for products on, let's say the HTTPS port, top product, yeah. Right. And so may you know Fritzbox HTTP config? I do not know. So what we have here, several hosts. Oh, one with a webcam, yeah. So if this is what you are looking for, here is a map of all webcam that I know in the world. So well, back to our slide. So these are just results on the internet, and you can do the same inside an enterprise, but the results are quite different. Why? Because in a film, hosts tends to be more homogeneous because of policy inside the firm. So, for instance, you can have address attribution policy with some subnetworks which are reserved just for workstation, other one just for servers, and maybe a given byte is just for routers. So when you have an anomaly, it might be very worse. You don't have your classic. You have a server or workstation which is different from what we have in the whole enterprise. So this is not normal. This is maybe the hacker which is already here. So what we can have as a group, we can have workstations, of course, printers, production servers, proxies, and what we have as anomalies, you can have a client lost inside the server subnetwork, so with maybe privilege on its firewall rules, and maybe an interesting point, host to hack, maybe. A server which is not using your, I don't know, what mil dollar appliance. And so, if you want to see enterprise results, do not hesitate, give us an internet access, and we can freely scan your company. But we may keep the results. So, as a conclusion, why hunting, our approach during hunting through machine learning is, okay, let the cores do the big part, the bulk of the analysis, and let the expert deals with details. So, it's a way to be able to quickly parse a large number of hosts, area thousand of hundred of hosts, hundred of thousand, and you just a limited comprehension is required. You just have to know what the PCA is doing, or just why it can give you that it is interesting that the HTTP port that he prints the HTTP port on the first axis, and why he don't print the Modbus port. If you remember, for the Modbus scan, the Modbus port is open on every host, so it is not present. It is not relevant to keep it. So when you're using the PCA, it will not show. It will not give him a weight. So the results are quite promising, and during the future work, we are not machine learning gurus, so we have done a lot of errors. We are keep looking for a better algorithm, better modeling, and maybe enhanced visualization. Maybe we don't want to have to go through the analyzer CLI and the web interface, of course, because it can crash you. And maybe it will be interesting to, for instance, use the address space and as a color the cluster that you have. So if you have a client which is loose in the server address space, we will just see it directly because you will have a red point which is loose inside blue points. And we are looking also for scan diff, that is to say you do several scans or just two, and using the modelization that you already have, just diffing between two hosts. And we don't care about the time which has changed, but maybe if a port has been open or has disappeared, that can be really interesting. So thank you for your attention, and may you have questions.
Thank you. In the Camille algorithm, you need to give the number of clusters. If you take your data, you construct a graph, you could use algorithm to compute communities, which does not need to know how many communities you have, like Louvain algorithm. Can you do this?
Actually, you also have the DB scan, which do not need a number of clusters.
Yeah, but it's expensive.
Yeah, but it's very expensive to do. And in Camille, you have some methods like I think the elbow method, where you use you try with three clusters, then 4, then 5 extra, and you check the variance of the distance. Or I don't understand any of this, but
right, but the Louvain algorithm is
okay.
Quite linear. It's very fast. I've tried it on graphs with hundreds of millions of nodes. It's very fast.
Okay.
You just need a graph, and you have a graph with your data.
Like I said, you are not a machine learning guru, so
I'm not machine learning, but I try.
So let's try it. Yeah, of course we can. We can do it. Thank you.
Yeah.
So it just. I will not do this now, Matt.
So you said that you use Nmap for scanning the interior internet, but is it really useful? I mean, Nmap is not that fast. It's not meant for scanning the internet, the interior internet, because you have things like jumping between kernel space and user space. So you waste time getting packets and parsing them. So
yeah. Actually, you can use a pre-scan like a ZMap, which has been made to be very fast. So for the Modbus scan, you just run a ZMap scan asking for every Modbus port open in the whole world, and then you go with your Nmap scanner checking for each host.
So Zenmap is using a custom TCP/IP network stack, or does it use the kernel space?
I am not. It's forging, so.
It's okay. And do you know about Mascan, maybe?
Yeah. That.
Okay,
yes.
so that's
ZMap
okay,
or
sorry.
Mascan. So Yes, as I said before, we are not doing the scan.
Okay.
We're just taking the sample and and
Okay. Thanks.
trying our result on it.
Good question. Anybody else?
Yes, just a question. Thank you for this presentation. You have based your cluster computation based on open ports. Can we consider to have other inputs like traceroute results or hostname or other inputs to compute the clusters?
Yes, definitely. You can add a lot of new information in the database. I don't know if you hear me. The most information you give, the more accurate the result you will have, but you still have to remember that it's dangerous to add some information, because if you consider yourself that this information is relevant, then you will change the way the algorithm behave. So we'll have to try, watch if it's relevant and the results are okay for you, and then you implement it and you add this. You can do with the IP address, you can do a lot of stuff.
Actually, for the enterprise results, if you may want to take in account the IP address, for instance, to find a client lost inside the server. What we do not do on a random scan on internet, because it's nonsense.